I'll wait a little bit for folks to stream in, and then I will get moving. I'm kind of expect not a huge attendance today, but we'll see what happens. A minute or so. If you got any questions or anything like that, feel free to let me know. I'm just kind of lurking here. Okay, I suppose I can just go ahead and get started here. So, as I'm sure you all know, today is the last day of lecture in this class. You're already done, unless you decided to do the extra credit assignment. Been done for a little while. If you do the extra credit assignment, sort of turn in at your convenience. I'm not sure when Breon's going to go through sort of the final grades and stuff like that, but probably not a big hurry. If you have any worries about grades or anything like that, you're probably fine. But if you do have questions, go ahead and shoot an email, CC Breon too, so we can check on it. Other than that, yeah, we're gonna kind of wrap up today with some mostly fun and useful stuff. So what we're gonna look at today is a bunch of different things, actually. I'm going to start by talking about working with model results. So we showed you a little bit of working with model results way back in week 6 with the loops, and we kind of extracted some stuff, did some cross-validation and things, but that was sort of some nuts and bolts stuff. Well, what I'm going to talk about today are sort of modern methods for extracting things from our model objects and also plotting results from models and then getting results from models into nice tables in your documents. Things you'll probably all want to do at some point. Okay, so we'll spend about the first half on that. The second half of the lecture today is going to be a rant about reproducible research and sort of best practices in scientific programming. So I'm just going to kind of talk about the basic ideas of reproducible research, why it's a good thing, and then talk about sort of best practices you can follow to make your research reproducible, but also easier to manage and better, more reliable, that sort of thing, easier to share with people. And then I'll really briefly wrap up the course, give some plugs for some other courses, that kind of thing. Okay. So first thing we're going to do today, we're going to work with model results. Okay, so the first thing to know about with working with model results is that there's no slide before. Okay, really? Yeah, there we go. Okay, it's weird. My slide seemed, could have sworn that was the other order around. Okay, first thing I want to introduce is this package called Broom. Broom is one of the most useful packages for dealing with the output from models. Even if you don't directly interact with it, it's probably under the hood of a lot of things you would use that would convert your model results into something nice, like a plot or a table. So Broom is this package that sort of sweeps up or tidies up the output from models like LM and GLM, but Broom supports a really wide variety of models. Basically, every large commonly used modeling package has routines or methods for Broom. And so what Broom will do is, provided a model, if you use the tidy function in Broom, it will create a data frame summary of the model results. I'll show this in a minute, but basically it will create a data frame instead of a list object, a data frame that contains your parameter estimates, your standard errors, and a bunch of other information on it. This is nice because it's really easy to plot in ggplot a data frame. It's very hard to plot and work with a list. So Broom produces something you could huck straight into a ggplot to make like a dot plot or something like that. Next main function in Broom is Augment. What Augment does is, provided a model, it will return the original data used to fit the model and add a bunch of columns to it that describe things like fitted values for every row of the data, leverage statistics, stuff like that. I'll show it in a minute. The last one is Glance. Glance provides a single row of fit statistics for a model that you give it. So you get one row, and then each column is things like the R squared, adjusted R squared, AICs, BICs, all that kind of junk. The nice thing with Glance, though, is that since it provides a single row of fit statistic for one model, if you give it a ton of models, it will provide a whole bunch of rows of those fit statistics to allow you to compare lots and lots of models really quickly in a data frame. Okay, so let's see these things in action. So, like I said a second ago, LM and summary on objects like LM will produce a list as output. As I've tried to sort of emphasize throughout this class, lists are very powerful, but they also suck to work with. Nobody really likes working directly with lists unless they're a pretty old school R programmer. For the purposes of this class and the stuff I've taught in this class, list objects cannot go directly into most, for instance, tidyverse stuff, and also they can't go directly into ggplot. So if I do something like this, where I go ahead and run a linear model, this is just some made up data built into these slides of y with a numeric variable and a factor variable, some data, and I get a summary on it, we get some sort of output that looks like this. This is a special print method of a list object, and it contains a whole bunch of different things. The call used to generate the model, information on overall model residuals, the coefficients in the model, some information on how to interpret them, and then a bunch of other junk like this overall model fit stuff, R squared and things. Okay? This is a list object. This is a nice output for you to look at, like in your console, but it's not the sort of thing you would ever put inside of an actual document you'd hand to a normal person. Okay, so another thing about model output is that even very similar statistical methods, like on the previous slide, LM, and on this slide, GLM, they produce different output across even very similar models. So here I've done a GLM of Y on the same variables using the same data, but here it is a binomial model with a logit link that is a logistic regression. If I get a summary on this, it looks pretty similar, but it is in fact not the same output as the prior slide. Some things you might notice that are different here is that it says, for instance, deviance residuals here instead of just residuals. In the coefficients pane down here, the standard linear regression says t value. For this, it is a z value, and it has a bunch of different information down here. Okay. Well, the thing is if you attempt to convert the output of these models into some sort of uniform format for you to work with, you'd have to write different code for every single different model you run, because all the columns and things are named different stuff. The lists have different lengths containing different things. It would be really annoying to have to manually write code to handle all these different things to allow you to compare across models of different types. Okay? Well, the nice thing about Broom is Broom doesn't care what kind of model you give it. It spits out the same output no matter what model you give it. So what we do is we take a model like our LM we fit a couple slides ago, our linear regression, and then we say, let's tidy it up. The output now is going to be a data frame. There's less information here than the summary method I showed a couple slides ago, but this is basically most of the things you probably actually care about. So what we have here is it outputs a data frame that is a tibble, 4 rows, 5 columns. It has one row for each term in the model. That's an intercept, a numeric variable, and then one row for each included level of the factor covariate. So factor 1 here had levels A, B, and C. A is a reference category, so it's omitted. And so these are the levels for B and C. These are the same parameters we saw right here. num1, fact1b, fact1c, the intercept. Okay. And then instead of saying like coefficient, standard error, z value, or whatever, it now just says generally an estimate, a standard error of that estimate, a statistic, the statistic being a t-value, a z-value, or whatever your model outputs, and then a generic p-value. So for frequentist models, anyway, you get this stuff. Tidy does support Bayesian models, and it does have a different output for Bayesian models, as one might expect. You have to tell to give you things like posterior modes and stuff like that. Anyway, the thing about Broom is it supports a ton of different model types, and every one of those models has a slightly different method. If you'd like to know how to run tidy for a given model you want to work with, you don't just do $tidy. You'll do something like $tidy.lm, and that will give you the help file for tidy specific to linear model objects. If you go into the help for Broom as a whole, you'll find that there are a ton of these different tidy functions going across many different packages in R. And the reason for that is that you have to do something different behind the scenes to get all these values. So what Broom is doing all that hard work it would take you to do this manually and just spitting out something nice regardless of the type of model you're working with. This is great if you work with lots and lots of different types of models and you want to sort of treat them all similarly. Okay. So as I said before, every model you give to tidy will produce basically the same output. So you'll notice here on this first slide, I did my linear model and I did tidy and I get term, estimate, standard error, statistic, p-value. On this next slide, I took my GLM, this is my binomial model, my logistic regression. I tidy it, I still get a term, an estimate, a standard error, a statistic, and a p-value. It's exactly the same columns. That means it's up to you to figure out whether you should be comparing these numbers to the numbers on the other sort of tidy output. But the nice thing is it's all exactly the same. So you can write functions and things that will handle models of any kind, put them into a ggplot, do whatever you want. This is really nice also if you run lots and lots of models and want to compress them onto a single data frame, like all of it, and compare them across. You can do that because they're exactly the same sort of dimensions. Okay. So the next function built into Broom that's kind of useful is glance. Glance produces data frames of fit statistics for your models. This is the kind of thing most useful if you run a lot of models, but I still sometimes use it when I'm running a single model. So if I say something like glance, my linear model 1 object, it's going to spit out a data frame with 1 row, because I only gave it 1 model, and 12 columns. The 12 columns are going to contain, for that model, its R² value, adjusted R² value, the sigma value, like overall model error, the statistic, which is for a standard linear model, an F statistic, the p-value for that statistic, the degrees of freedom, the log likelihood, the Akaiiki information criterion, the Bayesian information criterion, model deviance, which is actually the what you'd get if you ran it as a GLM linear model instead of a OLS linear model, degrees of freedom for residuals, and the number of observations in the model. Tons of information and sort of all of your most basic fit statistics you might want. This becomes really useful if you run like 50 models and you want to see which one has the best AIC or BIC. You stick them all into one data frame and then arrange it by AIC or BIC, and you can see what does best. Okay. The next function in Broom that's useful is Augment. Augment takes values generated by the model, like fitted values, and adds them back to the original data. So if I say something like, take my linear model 1 and augment it, here I'm just going to look at the first 6 observations because that's the default it had. It actually returns the entire data frame used to fit the model. What we're going to get is the original values of all the variables in the model, like yn, num1, fact1. This is the original data here. Then what it's added are all these columns that begin with a period. These are the fitted values, the residual for a single observation, hat values, sigma values, Cook's SD values, standardized residuals. So these sort of things over here are really useful for figuring out what observations might be outliers in your data, right? So Cook's D values over here are a leverage statistic. So our hat values, and technically standardized or studentized residuals. Right? So Augment can give you some other stuff too if you want it. But this is the kind of thing I like to do if I want to get, for instance, you know, my fitted values here, plot them in a ggplot against my actual original y values. I could put my fitted values on the y-axis and my original values on the x-axis and make a plot to look for instance, heteroscedasticity in my model or something. Augment is sort of useful for doing this. And the neat thing with Augment is, again, it works on nearly every common model type in R. Pretty handy. One of the only model types it doesn't work super easily within R are fixed effects models from the fixest package. And I think that's because they don't return the data frame inside their model object. So you have to manually give it the data frame back. Slight annoyance, but usually Augment does what you need. Okay. So Broom is powerful. The real advantages of using Broom become a lot more apparent when you start running multiple models at once instead of a single model. Here's a slightly advanced example that uses some things I do not teach in this class, but if you ever want to do something like this, you can look at the code I just wrote here and figure out how to adapt it. So what I say here is I begin with the original data I'm working with. XDAT here is just a big data frame with some categorical and numeric values. And then I say, I would like to nest by FAC1. So what nest by does is it takes this data frame and breaks it up into separate data frames by values of FAC1, but then nests them into sub-data frames as list objects. So what this would produce here is a 3-row data frame where one column contains a list column where the data frames are embedded in each element of that list. That's a weird, complicated thing, but it's really useful for doing this next thing. I then say, and then I'd like to mutate a new column called model, where the column is going to be a list containing a linear regression of y on num1 and fac2, where my data is data. What is data? It's the nested column containing all of the data broken up by fac1 generated by nest by. So this is a way to use mutate to run a model and return a model object where each element of so in each row will be one model output. Then I can say summarize by tidying that model column and then drop the groups here because I don't want them nested on fac1 anymore. My result is going to be something like this. These are the value of fac1, the variable I nested by. Within each value of that factor variable are all of the coefficients, standard error statistics, and p-values for models run within each one of those categories. So this actually, by nesting on fac1 and running a model, it ran 3 models. This is one model for all the data where fac1 is A. This is a model for the data when fac1 is B, and this is a model for when fac1 is C. You could imagine if instead your factor variable had 100 levels and you wanted to run one model inside each of them, you could use this exact same code and you would get a data frame that would have 3 rows for each model repeated 100 times with all the coefficient parameter estimates within each one of those categories, which you could then do stuff with in ggplot or in whatever in dplyr syntax. Right? So this is a fairly complicated thing, but this is sort of the where you could go deeper and further with running multiple models and sort of parallel operations using dplyr. Turns out I can do a lot more than I teach in this class. Okay. So that's all I've got on Broom. Does anybody have any questions about working with Broom, using it for stuff? It's probably the most useful package for extracting model results and turning them into something usable. And it's in fact under the hood of much of the other functions I'm going to show here today. Okay, keep moving on. So let's talk about plotting results from models. So I've used in a lot of ggplots in lab and some in lecture, I've used the geometry geom smooth. Okay, so geom smooth on a ggplot generates smoothed conditional means through your data. If you don't give it any options, it will usually generate a type of curve called a low S curve, which is a type of local polynomial regression, or it will return a generalized additive model result, which is another type of a spline. Okay. The thing is, though, is that low S curves and GAM models are smoothed conditional means. Well, a standard regression model is also a conditional mean model. Things like ordinary least squares and generalized linear models also tell you a conditional mean given some value of x. The difference between an ordinary least squares or standard linear regression model and a GAM model or a low S curve is that low S curves and GAM models bend. They kind of flex through things, where linear models are straight lines, at least on some scale. Okay? But they're still conditional mean models. We can use geom smooth to a ggplot to add a layer which will depict any kind of bivariate relationship you want. So for an example here, I'm going to load up the Gapminder data from week 2, way back in beginning of this class, and show you how to sort of display model results on a ggplot. Okay, so here's an example. What I say here is we're going to make a ggplot. Our data is going to be the Gapminder data. My aesthetics are going to be year on the x-axis, y is going to be life expectancy. Color is going to be continent. And by doing color continent, it's actually going to break the data up into different bins, essentially, of data, one for each continent. I then say, I'd like to do geom point, a scatter plot. I jitter the dots so they don't all overlay each other. This is just sort of making it so instead of being all in one line for the year, they're spread left and right a little bit. And then I just say geom smooth. If I just say geom smooth here, it's going to draw a slightly bendy line through all of the points for each one of the continents. Okay? In this example here, geom smooth is producing, I think, a low S smoother because there's less than 1,000 data points within each group. If you have more than 1,000 data points, it's going to do a more efficient GAM smooth. They're basically the same thing. Okay? So this is a conditional mean model. This is, in fact, a model. This is just a flexible sort of polynomial model displaying the relationship of life expectancy by year. Okay? We've done this a bunch. You can change this, though. So if I take the exact same syntax for the ggplot, but in geom smooth, I instead say my method should be a generalized linear model, and my formula should be y tilde x, that is the y-axis variable regressed on the x-axis variable. This is now displaying the results from a generalized linear model, which defaults to being a linear regression model. Okay, so this is the same sort of basic model as the previous slide, but because it's a standard GLM model, it's perfectly linear. The line is perfectly straight. This is the exact regression slope and line you would get by running a GLM model for each one of the continents separately. This is its slope you would get. These are sort of what its predicted values would be along the line, you name it. Okay? So this is how you can run and get results from a bivariate model. If your model only has 2 variables in it, you can just do geom smooth and say make a linear regression, and it will plot the expected values for you. That makes sense? Nobody's on camera, so I don't know if anything makes sense. Nothing makes sense anymore. Okay, next. Okay, you can, in fact, alter and do polynomial models in here. So if I take the exact same syntax I just did, it's the same ggplot, I still say geom smooth, I still say it's a GLM model, but I can alter the formula. Here I say my formula is going to be y regressed on a second order polynomial of x. This is a quadratic model. Poly x2, by default, it's actually generating orthogonal polynomials, but it's exactly the same result as you would get by doing x plus x squared in your formula. So what's being displayed here is a quadratic functional form of y on x. So you can fit polynomial models here. It's still a bivariate relationship. It just happens to be that for this variable, it has 2 parameters on it. It has a linear term and it has sort of a curvy quadratic term. Okay? So you can also do polynomial models. I could also do x cubed or whatever. I could do as many orders of polynomial as I want. So if all you've got in your model is an outcome variable, a single predictor and polynomial forms of it, you can also just do that in geom_smooth and ggplot, and you'll get your fitted values, your nice fitted regression lines. Note here that this actually looks a lot like the smooth that we did with the lowest smoother at the beginning. If I go back here, the lowest smoother basically looks like that. It has some kind of curves going like this, curves, curves, curves. It can basically, in the quadratic one, replicate those almost perfectly. So you could do something like this and get basically the same result as the lowest smooth. Okay. So the thing is, well, what if you want to do something more complex than a bivariate model? What if you got any kind of more complex model? Maybe you have something like a nonlinear probability model. Maybe you've got multi-level models. Maybe you have more than one variable on the right side of the equation. If you want to do any of those things, you're going to have to move to something more advanced than just geom_smooth. Okay, so before we do that, I'm going to talk about a little bit of vocabulary that will help you hopefully think about these things and especially search for help for doing these things. So the idea here is we're often interested in what might happen if some variables take particular values. So that is, what would our outcome look like, our y variable? What would it look like if some of our x variables were at particular values? Maybe even those particular values don't even appear in your actual data. So when we set some variables in a data set to certain values and make predictions with them, we refer to those values as counterfactual values, often just counterfactuals. So they are values that perhaps don't exist in the real world. They are counter to fact. They are something that we are sort of imagining and posing as a hypothetical situation where we'd like to imagine what might happen if these values were true. Okay, so for example, let's say we knew nothing about a new observation of data. If we were going to get some new observation of some particular process or something that's occurring, something's going to come in. Our prediction for that estimate might just be assuming every variable in our model is at its mean. We might be like, well, if I know nothing about an observation, I'm going to assume that they are as close to average as I can, because maybe that will make me least wrong on average. So it might say, counterfactually speaking, let's set every variable to its mean and then see what the predicted value of that would be. It may very well be the case that in a data set, there's no observation that sits at the mean for every variable or even near the mean for every variable at the same time. But it's still useful for describing sort of an average trend in the data. Okay. Sometimes, though, we might not want the mean for every variable. We might have very specific questions which require setting possibly many combinations of variables to particular values and then making estimates or predictions based on those values. Maybe what you want to see is what would be an expected value when x1 is equal to 5, x2 is equal to 10, and x3 is equal to 0, but then across a ton of values of each one of those variables. These are all counterfactual scenarios. We then want predicted values from them. Okay, so providing specific estimates that are conditional on a bunch of values of covariance is a really nice way to summarize results for models, particularly for models with unintuitive parameters like logistic regression models. So if you were talking to someone and they tell you that logistic regression results are intuitive to understand numerically, and this is either in log odds or odds ratios, that person probably doesn't know what they're talking about, or they're an economist or somebody who actually thinks in log odds at times. Okay? Turns out logit models, for instance, and many nonlinear models do not have particularly intuitive parameter estimates. Okay? So people will often say something like, oh, an odds ratio of 2 means something is twice as likely to occur. No, that is not true. It could be twice as likely to occur, but it could be much less than twice as likely to occur or much more than twice as likely to occur, because odds ratios are not probabilities. So giving people odds ratios, unless you work in epidemiology and you focus on very rare outcomes, odds ratios are basically useless and should not be provided to people. They are not directly interpretable the way most people try to. Log odds are also not particularly interpretable because they're even worse. They're the logarithm of those odds ratios, okay? They're still weird and multiplicative. If you're going to provide the results of a logistic regression model to somebody, you know what's a lot better to do? Give them a probability. Give things in probability terms. But logit models are not linear in the probability, so the thing you have to do is generate counterfactual values and provide predicted probabilities at different levels so that people can get something useful out of it. Oh, another useful thing to know to further ruin your day if you ever work with logistic regression models is it turns out that if you have a logistic regression model and you add a variable to it and the coefficients in the other variables change, it doesn't actually mean they're different. So the thing about logistic regression models people don't realize is they actually have sort of a unobserved, unmeasured constant built into them that multiplies the size of the coefficients based on an inverse proportion of the error in the model. This means if you add a new parameter to the model, all the coefficients will necessarily always change. So it doesn't mean, for instance, introducing a new variable shows a case of mediation when the parameters change. Don't interpret log odds, don't interpret odds ratios, don't compare log odds between models unless it's only the exact same variables. Okay, good things to know. If you're interested in more information on that, I can send you some great papers. Anyway, so what we want to do here is we want to get some useful parameters out of these things. Okay, so one way we can do that is with the package ggfx. One second, the cat has opened the door. As soon as I close the door, she will return and open it again. Can't tolerate a closed door in this house. So let's talk about the ggfx package. Okay, so if we want to look at more complex models than what ggplot can handle, we can use ggfx to create and plot tidy marginal effects, which are essentially effects calculated from counterfactual values. So what ggfx will do is it will generate nice, tidy data frames of ranges of predicted values, which you can then feed straight into ggplot to plot model results. I'm going to focus today on two functions in ggfx. The ones I'm going to focus on are ggpredict, which computes predicted values for some outcome variable or variables at the margins of specific x variables. I called it. The cat had to open the door again. Good cat. Okay, so computes predicted values given specific x variables, basically. Good cat. So then I'm going to talk about the plot.ggfx method. This is a method of the plot function that automatically plots the results from ggpredict calls. Okay, so I'll show you what this looks like here in just a second. You'd load up ggfx. Then what I'm going to do here is I'm really quickly going to simulate out some data with some known relationships. It's not important what I'm doing here, but I don't like to hide anything from you. So if you want to know how I've simulated a bunch of data to do something, this is the code necessary to simulate out some data with a bunch of numeric and factor variables, which have some sort of relationship between the x variables and the outcomes. Okay, it's a good idea to learn how to simulate data as you get deeper into quantitative analysis so that you can, for instance, create data with a known relationship in it, run a model on it, and make sure your method can actually recover the numbers you're after. That's sort of a common practice in more advanced papers and things. Anyway, now let's do some predictions with this. So when you run ggpredict on a model, it will produce a data frame with a single row for every unique value of a supplied predictor that is some independent variable, or it will create evenly sort of spaced values of it if it's a continuous variable. What each row contains will be an expected or estimated value for that outcome, the dependent variable, plus some confidence intervals. This is how it works. If I say, I would like to run a linear model of y on some numeric variable and some factor variable. I assign it to LM1. I then say, I would like GG predictions of my linear model 1 object, specifically over a bunch of different values of the num1 variable. So what this is going to do is it's going to hold constant the fac1 variable, vary the num1 variable, and give me a bunch of predicted values for the y outcome variable. I'm going to assign this to LM1 estimates. If you wanted to, instead of getting confidence intervals, get prediction intervals, you could just add interval equals prediction, and it will give you the wider intervals you'd get from prediction intervals. Okay. So this is what its output looks like. If I look at lm1est, it's going to produce a nice printed output that's going to say these are predicted values of y. X is the num1 variable, and these are different values of x that it generated predicted values over. So it went and looked at the range of the x variable and started at pretty close to its minimum value and went to pretty close to its maximum value, and then picked a bunch of evenly spaced values from the minimum to the maximum. And then it gives predicted values of the y variable at each level of x and a confidence interval for that predicted value. Down at the bottom, you see it says, we have adjusted for the fac1 variable has been set to its reference level. You could specify different reference levels or specific values of this, which I'll show in a minute, but by default, it just sets it to its reference level. Okay, you might be like, okay, well, so I've got all this stuff, but how is this useful to me? Turns out it's super useful, because all I got to do is say plot that object, and it spits out a ggplot depicting that relationship with its confidence intervals. So this is the plot method I was talking about. All I have to say is plot any ggeffects object, and it recognizes it as a ggeffects object, and it runs its own plotting functions. Those plotting functions generate something that looks like this. They put the appropriate variable on the x-axis, the appropriate variable on the y-axis. They change the title to be predicted values of yn. They draw a line and also generate smooth confidence intervals, accurately getting the uncertainty across all values of x. So this right here is the predicted relationship between x and y and what predicted values of y would be at all the values of x. That's how dumb easy it is with ggeffects, and why I usually try and show people this package anytime they come to me to plot predicted value plots. This is the easiest method I have ever seen for doing anything of this sort. Do it this way. Okay. So far makes sense, nothing too crazy going on. We're going to complicate this a bunch because this is a really cool package. It does a bunch of other crap, but basically, this is the simple thing you can do. So if anybody, your advisor, or somebody in your committee is like, I would like to see predicted values across a range of a variable, you do that, you add one line of code, boom, you got it. Okay. So thing is ggeffects can take more than just linear regression models. It can take nonlinear models like logit models. It can take random effects models, mixed models, all sorts of things, all sorts of models. And it also has some additional features for doing things like subgroup analyses. So if I do something like this, I take a generalized linear model of my binary y on 4 variables, and then I say family binomial link equals logit. This here, of course, is a logit model. So logit models are often hard to visualize unless you convert them to probabilities. If I pipe this logit model into ggpredict and say, the terms I'd like to vary over is a numeric variable 1 and factor variable 1, and then plot it, what it's going to do is put the first variable you name on the x-axis of the plot. It's going to turn the second variable into multiple lines, which are also colored. So for instance, this is at values of fac1 equals A, fac1 equals B, fac1 equals C. And then it's converted y into probability scale instead of log odds or odds ratios. These are in probabilities, which people can actually understand. So right away, you can see some power here. You can provide multiple variables at once, and it will provide multiple lines across all these things. If, for instance, num1 and fac1 have an interaction term between them, it will correctly model that interaction and produce lines of differing slopes across that factor too. It's very smart, and it knows the way your model works. Okay. So it has some additional features to make a plot like that a little bit more usable. So if I run the exact same code, my logit model, I can add to my plot function at the basically ggpredict and then pipe it into plot. If I say facet equals true, instead of plotting all the lines on top of each other, it plots each line on its own facet where A, B, and C are the levels of this variable fac1. So it also knows how to facet these things out to make them more legible if, for instance, all your lines overlap like this and it makes it hard to read. Okay, so it has some additional functionality like that. Do I have some more on this? Yeah. Something else which I'm not sure, no, I do cover it in a minute. I'll get there in a second. Okay, so other things ggfx can do. ggfx also lets you set specific counterfactual values for each variable in that terms that you assign. So if I take my same logit model, but then in ggpredict I say, my terms should be num1, but I specifically want predictions at num1 equals -1, 0, and 1. And I want predictions for fac1 at only levels A and B, and then the same plot. I only get the predictions at fac1 equals A and B, and then my x-axis only runs from -1, 0 to 1. So this lets us set very specific values for our predicted values. So maybe you've got something in mind and you're like, all I care about is this range from here to here. You can specify that range in the terms argument and it will provide it. Again, if your advisor or somebody asks for something like this, that's the syntax to do it. It's very easy to do. This also lets you make values beyond what your data show or narrower than what your data show, which is nice if, for instance, the minimum and maximum in your data are actually kind of outliers and you want it compressed to a narrower range. So you could pick representative values. Okay. Question. Can we change the names of variables in the axis in ggpredict? Oh, yeah. You know why? Because this is a ggplot. Literally everything you can do to a ggplot, you can just plus and add on to it. So it's hyper flexible. You don't have to put all the stuff in the plot. I'll show you in a second, I think, that you can just plus and add on xlab, ylab, ggtitle. You could theme it. You can do anything you can do to a ggplot because this is just a normal ggplot. So all those skills we've learned over the term of ggplot, you just bolt them onto this and it does the job. Okay. So you can also do representative values. So instead of specifying exact values for things, you could also say something like, I would like GG predictions for my num1 variable at its mean and plus and minus 1 standard deviation. This down here is its mean minus 1 standard deviation plus 1 standard deviation. And then here at num2 between its minimum and its minimum value being this -7.7 and its positive this 8.6. So it also has these specialty little things you can put in brackets to automatically calculate values you might be interested in. So here's a great question. To do the range of values, is it 1: that? I think it is. I think you can just give it the same sort of syntax like that. I'm not 100% positive. ggfx has fantastic documentation, though, so it's really easy to look it up. Okay. So another thing, ggpredict does not only do line plots. ggpredict is smart. So if I do something like this, run a linear regression of y on 2 factor variables, and then say ggpredict my terms equals 2 factor variables, it doesn't make sense to plot a line plot over a factor. It's categorical data. ggpredict knows this. So instead, it spits out a dot plot with error bars when you give it categorical predictors. So here, these are predicted values of my y variable at all the different levels of factor 1 and the different levels of factor 2. So for instance, I could say my predicted value of 1 when fac2 is no and fac1 is C is about 3.75 or 3.8 with this confidence interval. These are nice dot plots. This is the kind of thing you might provide, if you're actually putting this in a paper. In fact, I think I have an example of this. This is actually, if you remember all the way back to my ggplot lecture, I actually showed a couple sort of dot plots like this. It's the same basic idea. I think I've even got it embedded in these slides here in a minute. Okay, so you can do predicted values. It'll give you dot plots if you give it factors, which is a reason to store your data as factors or categorical data if they actually are instead of numeric values. ggpredict will then know how to plot. Okay, so some notes on this package. It's a big package with a lot of functionality, and it's always being updated a lot too. It can do a lot of different things, works with a lot of different models. If you're interested in it and you want to use it a lot, I recommend checking out its package Vignette and going to its GitHub repository, and going to it also has a dedicated website for it. So other things it can do I didn't show. It can get predicted values also for polynomial and interaction terms. If you have complicated models with nonlinear terms in them, it will happily plot correct predicted values for them, and importantly, correct confidence intervals for those things, which can sometimes be hard to produce with other methods. Like I said, it can get predictions from dozens of other packages, most of the major packages out there for models it can cover. And also, like I said, all the output from ggfx is ggplot objects. So you can add on to it with literally any ggplot functionality that you know. You can just tag it right on. So if you need to do something more complicated than what ggfx can do, I do have some syntax, which is a little bit out of date. It still works, but I think it's kind of a crude method to do it for doing advanced counterfactuals. That is doing exactly what ggfx does, but doing it manually, including doing the math yourself. So just as a quick example, in these counterfactuals, I will actually show you how to use real data to produce plots that look like this. This is actually taken from my 2018 City and Community paper on differences in probabilities of probable cause and arrest by the Seattle Police Department by the race of people they contact and the race of people who called the police, that sort of thing. The problem with this is this was a model with like a 3- or 4-way interaction in it, which ggfx couldn't handle. So I had to manually generate a dot plot like this. So you can actually see the syntax necessary to generate that manually. And I also show you the math that explains how it works, which is kind of useful if you want to know how to do this yourself. Turns out the math is actually pretty simple. And if you've ever taken Chris Adolph's like maximum likelihood estimation class, this is based on the same math that he has in there, except this method is a little bit easier to do. Okay. So useful stuff. Anyway, and that's also how I generally do all of mine. I actually don't use ggfx too often. I very much like to manually calculate things myself because it allows me to do things like use different variance covariance matrices across my different predictions, which is the kind of thing nerds do. Okay, so next thing is making tables. Anybody have any questions there on ggfx or anything related to that before I move on to making? Oh, non-content related question. The etymology of the GG prefix, just curious. So GG actually was originally grammar of graphics. The grammar of graphics was something not created by like Hadley Wickham, but by Wilkerson, I think, before Hadley Wickham, who basically came up with this sort of philosophy and logic for how visualizations could be assembled. And then that gave way to like Wickham and other people building the ggplot infrastructure. ggfx uses the GG prefix because it's built on ggplot for making all of its plots. So a lot of packages that are built on top of and use ggplot put GG in front of it to signify that they're part of the ecosystem of ggplot. Okay. Though you don't have to use ggplot with GG effects, you can actually produce the data frames it generates that go into the plot and put them into something else if you want. Okay, so let's talk about tables. Many ways to do tables in R. I've shown you mostly bad ways in this class. I'm going to show you fancy ways today. So speaking of bad ways to do tables, I have shown you how to use Pander in the past to generate tables in your Markdown documents. The reason I showed you Pander is Pander just works for everything. Pander is one of those packages where it's kind of old, it's crude, it's not very flexible, it's not built on modern R tools, but damn if it can't make a table out of anything, okay? So I showed you Pander because when in doubt, you can probably make a Pander table out of it. So Pander handles basically all types of basic R models. It doesn't handle more modern models, but whatever. Wow, more modern models. That fucking broke my brain. Okay, anyway. So here's some examples. So we can take Pander and give it, for instance, a linear regression object. If I create a linear regression model, LM1 from earlier, and I put it in Pander, Pander will generate a very simple, somewhat ugly markdown table. It will have the estimate, standard error, t-value, p-value, intercept, weight, whatever. It will also say sort of give it a title to this, MPG on weight and horsepower, because that was the model I ran to get this. This is actually exactly what you would see in the summary output of LM1 in the coefficients area, because all Pander is actually doing is running summary on LM1, extracting that object and converting it to a markdown object. It's not doing anything fancy, it just spits it right out. But it's really fast and easy, and if all you need to do is produce a memo and it doesn't have to be pretty, there's basically nothing faster than Pander. Okay. You could also give Pander instead of LM1. You could say summary LM1 Pander. It's going to give you the exact same output, except with added number of observations, residual standard error, R squared, and adjusted R squared. If you want those things, just do summary LM1. It will give it to you. Okay. It's still an ugly basic markdown plot, but our markdown table, but it does the job. Okay. So Pander is good for very basic, rough, fast sort of things. It is not going to be producing you something that I would call publication ready in any way. If you want to make something that looks nice on your website or is going to go into a journal article, you're not going to be using Pander. You're going to use something else. So I'm going to talk today about a few different approaches for making nicer tables. The first thing I'm going to talk about is the GT package from RStudio, which is a general table construction package. It's very powerful and flexible. It's also a little bit new, so it doesn't quite do everything yet. Then I'm going to talk about model summary, which is specifically for creating tables out of your model objects. And then GT summary for creating data summaries, summaries of your data. GT summary can also do models, but I think model summary has a better syntax for it. I will also briefly talk about a package that I have recently come to love the way I love few other packages called Flex Table. So we'll get there. Okay, so the GT package. Okay, if you need more customizability or different output types from tables, I like RStudio's GT package as a whole ecosystem for generating complex, very pickily designed little tables out of data frames. So for my example today for the GT package, it turns out, and I cannot believe I only discovered this like a year or a year and a half ago, the dplyr package has built into it Star Wars data, and I am a giant nerd, and this made me very happy. So anyway, in the dplyr package, there's a data frame called, well, actually not a data frame, it's a set of data frames, including, it's a data set like this with a bunch of list columns with sort of sub data frames. So anyway, I load up library GT. Then I take my Star Wars data. I unnest all of the films, all of the starships. I filter down to only The Empire Strikes Back. Select particular columns about characters. I get the distinct names of characters, only one line per character. And then the way this came out, for some reason, it was convinced Obi-Wan Kenobi had a Jedi starfighter in The Empire Strikes Back, and I had to correct that error. Then I assign this to TES cares here. I glimpse at my data frame, and this is what I got. I have 16 rows of data, which are different characters in The Empire Strikes Back, 5 columns of data, which is the name of the character, the species, their associated starships, and then the mass and the height of the character, because apparently you need vital statistics for fictional characters. Okay, so we're going to work with these data. So if I just say The Empire Strikes Back characters and then GT them, the GT function in GT will generate a table. It will just render that data frame as a simple table in Markdown. So the default table is going to look something like this. You'll see it's got the name, species, starship, mass, and height columns. Everything's sort of spit out. This is the entire data frame of data. Nothing too fancy here. In fact, you'd probably get something pretty similar by spitting it into Pander. Next, what we're going to do is we're going to, and notice this is not in GT. If I say, take my TES characters and then group by the starships in the data and then send it to GT, GT, like many dplyr functions, recognizes grouped data. Once it's grouped, it breaks out all of the starships out of that column and instead makes them little categorical rows. So these are the characters associated with an X-Wing. These are the characters associated with no ship, TIE Advanced, Millennium Falcon, Slave 1. Okay, so what this has done here is it's figured out that I want to group on this column. And if I want to group on it, I don't want to display the column in my data. I instead want subtables, one table for each value of starships. So this is a subtable, this is a subtable, this is a subtable, this is a subtable, this is a subtable. This is just GT's way of handling groups. I think there's another way you can tell it to keep that column and still group if you want. Next, what I'm going to do here is I'm going to say for the name column, I don't want it to have a name here. So here, what I say is GT row name column equals name. What this is going to do is it will designate the name column, which you see here, the name column, as row names. By designating it as row names, it removes the name of the column here and it divides them off from the rest of the data. So this is how you would handle unique identifiers in your data. If you've got something like maybe the names of states or neighborhoods or something like that, and you want to break them off to be like, that uniquely identifies my observations and everything else is data about that, you would give it a row name column and then it will set them off. So now we know, for instance, all of the data to the right of it pertains to this one particular character, but this stuff doesn't uniquely identify them on the right. It's purely aesthetic, but it makes the table look a little bit nicer. We see the previous slide, no divider, column up here. Now it's indented slightly, column sort of divider right here. Next thing. So what I want to do is I would like to add a title and subtitle to my table. So I say, I'd like to add a tab header. And notice here with GT, I just pipe things into new GT functions. So this is not like ggplot where you use plus. You just keep piping things together and adding them, and it will keep modifying the table. This is a little strange syntax, but it's actually really easy to use. Don't worry about the magic that makes it work. Just know you can keep using the same pipe and you don't got to use pluses. So what I say here is tab header. My title should be Star Wars characters, and my subtitle should be The Empire Strikes Back. What we get here now is the title Star Wars characters with a subtitle The Empire Strikes Back. Works just like GG title. Next, what I do here is I add a spanner. So if I say tab spanner, label equals vitals, columns equals the variables mass and height, it's going to add a spanner right here. A spanner will draw a horizontal line across the variables I name and then add a little title above them. So this allows me to specify in the title that these particular columns are grouped together in some way, specifically their vitals or vital statistics of those particular characters from the movie. You can see before, they just sat there looking like normal columns. Now it adds that little tab spanner. This is nice for a variety of reasons. You might have certain grouped measures you want to have in your data, or maybe you've got data where you've got something like a coefficient and a standard error across a bunch of different models. You could put a spanner across each of those pair things to show that they're from the same models or something like that. Okay, next. So what I want to do here is I don't want to be constrained by the original data variable names. So maybe I like working with variable names like mass and height, but I don't want them displayed that way. I can say add column labels where the mass column will be named mass in kilograms, height will be height centimeters, and species will just be capitalized. So here now the species column's capitalized, and then these ones have a little bit more information added to them, mass in kilograms, height in centimeters. This only changes the way they're displayed. It doesn't actually change them in the data. So as I go on, I can still refer to them as mass and height, but it's changed the way they're labeled in the final output. So table's getting to be a little bit nicer looking. Next thing. So for some reason, if you look on mass in kilograms, every single person in the Star Wars universe apparently has an exact even mass at kilograms, right? 0.0, 0.0, 0.0. But for some reason, Boba Fett is specific. Maybe Slave One has a scale on it that's actually accurate, and he can measure himself to 78.2 kilograms, and he just had to report that. Well, I probably don't care about that decimal point. You can do little fine formatting in GT like this. I can say, format numbers. Specifically, I would like to format the mass column and give it 0 decimal places. So this will format all the numbers in the mass column and specify that they shouldn't have any decimal points. It will just round them automatically to 0 decimal points. So you don't even have to modify the data in the data frame itself. You can do that formatting after the fact in GT, so you don't have to modify your data beforehand. Next, what I can do is, if I look at this table, we have species is left aligned here. Mass almost kind of looks right aligned. This one looks center aligned. I want to fix my alignments. So I can say here, if you see, I can say here, let's align some columns. So columns align them to be center aligned, specifically these variables, species, mass, and height. And now they are center aligned text in all the columns. There's a million of these little formatters for all sorts of different purposes that can allow you to very specifically tweak how everything in your table looks. So if you're a picky person like me, this is a very useful and powerful package. I have one more thing. Yes. One other thing is maybe what I want to do is reorder my data, but I don't want to reorder the rows. I want to reorder it by its groups. I can say here, change my row group order so that the groups X-Wing and Millennium Falcon come first, and then everything else stays in its original order because I don't care. So we put X-Wing first, Millennium Falcon, and then everything else remains in the prior order it was in before. So you can actually modify the row group orders and stuff if you want. There's a lot of this little functionality you can do on these tables to make them look exactly the way that you want. So now we can look side by side and see this was the original table we spit in when we just did GT, and the final output table over here on the right all formatted the way I want it. Okay? So this is a big improvement. It looks pretty nice. This table on the right is something I would be perfectly happy to have displayed on like a website or in a memo or something like that. This is a pretty good looking table, and it was done all with some sort of relatively straightforward syntax. Okay. So there's one caveat to the GT package at the moment. I'm showing it because I think it has the most potential to grow into one of the biggest, most powerful table packages, but it's still a pretty new package in active development. And at the moment, it's quite finicky with PDF output. It doesn't make LaTeX tables nicely all the time because LaTeX is very hard to put together. So they've sort of, they're delaying putting in full LaTeX implementation until they've stabilized the way that the package works with everything else. Because it turns out it's a lot easier to do the other stuff than it is to do LaTeX. Okay, so if you need nice looking LaTeX tables, as if might be needed for a really nice PDF file, I recommend looking into similar packages that work a lot like GT, but are slightly more mature. Those packages are Cable Extra and Flex Table. Lately, in particular, I've been liking Flex Table. Flex Table has some oddities and some limitations, but Flex Table is, as the name suggests, more flexible than any other R table making package. Okay, so like GT, the Cable Extra and Flex Table packages let you construct pretty complex tables in HTML or LaTeX or Markdown formats using an additive syntax. That is, you can pipe things together and produce something that looks good. Okay? So it looks a lot like dplyr. The one thing about Flex Table that's really cool is Flex Table produces really nice Microsoft Word tables. So if you're going to have your output be Microsoft Word documents, which a lot of people like to work in Word, I don't like to work in Word, but I use Word all the time. This is how I produce tables, say, in the Word drafts of my dissertation. I do it with Flex Table because it produces by far the best Word document output of any table package I've seen. Okay. If you want to edit LaTeX documents, now I think I've said before that LaTeX is a horrible thing. It is a terrible language. People who recommend you learn LaTeX are just trying to trick you into experiencing the suffering they experienced long ago. But if you do want to work in LaTeX and edit LaTeX documents, you can do pure LaTeX documents in R using Sweave. The Sweave document, which is a .rnw file type, is what came before our Markdown docs. So it turns out before these beautiful R Markdown docs we use in the class, everyone just worked entirely in LaTeX. So the entire ecosystem of R Markdown was created to not have to use Sweave documents and LaTeX. So please do not do this unless you must. Another thing, an alternative I recommend if you do need to work in a dedicated LaTeX editor, I actually recommend Overleaf, which is a fully online collaborative LaTeX editor. It takes care of LaTeX package management and stuff for you online. It also has built-in error checking and things. It's sort of a nice way to do it. Still, my first advice would be steer way clear of LaTeX. Okay. Anyway. Another thing, R Markdown also has support for a pretty good amount of LaTeX in it. For instance, you can see how I actually am obsessive about actually using the correct LaTeX logo. This is LaTeX embedded in the R Markdown document. R Markdown can handle most basic LaTeX equations too, stuff like that. So typically you don't even have to use a LaTeX doc. About the only time I actually use an actual LaTeX document in R is if I have to do like TIX images or something. If I have to make LaTeX generated flow diagrams and things, I actually do those by hand in Inkscape or Illustrator nowadays because LaTeX is a waste of my time and I know how to write LaTeX. Okay. So really quickly, this is an example. This is actually a table from my dissertation, one of my dissertation chapters. This is an example of a flex table in Word format. So this table is produced straight out of Flex Table, set to Word format. And notice something cool about it. This is a Word format table with frickin' embedded images inside the table. Flex Table can do crazy stuff. So it looks just like this in Word. It looks just like this produced in R. Yeah, so Flex Table can do some cool stuff. So I basically fed it the actual data frame of my observations of my data. And these are just the particular measure, their mean, standard deviations, minimums, the actual density plot of the variable and its maximum. These are nested hierarchical data. That is, I have 1,641 observations nested in 343 neighborhoods. I can actually display all of these summary statistics and my descriptives in a instantly generated flex table with embedded plots, which shows up beautifully in Word. Okay, yeah, this is crazy cool. When I saw that you could do these embedded little mini plots, I was first like, no way. And then I looked at the syntax. It's not the easiest thing in the world, but it was easier than I would have expected it to be. And you're not limited to densities. You can do some other weird stuff in there too. Okay, so Flex Table, if you want to do tables like this and you need to work in Word docs, Flex Table is probably the only really good way to go right now. And I actually like it a lot. I've converted over to Flex Table for a lot of tables. Okay. So next package I want to talk about, I want to talk about Model Summary. So Model Summary is a package that combines utility or combines functionality from Broom, from GT, from Flex Table, and Cable Extra to produce tabular summaries of basically any model in R. So it does it like this. So what Model Summary does is you give it a model, then it goes and runs Broom's tidy and other functions on it to get a data frame of those things. But then GT, Flex Table, and Cable Extra take data frames. So it sends that model output from Broom to GT, Flex Table, or Cable Extra, and then modifies its formatting a little bit. This is what I love about the R ecosystem. Somebody was just like, well, let's make this package talk to this package. And so they wrote a package that makes these two packages talk together. This is actually a really common thing in sort of the open source world, but Model Summary is a great example of it. So the neat thing about Model Summary is because it uses all these really general packages, it can do everything. So it can take just about every model output and it can produce as an output HTML, Markdown, LaTeX, raw text, and even image output. So it can automatically generate the table in something like a PDF or whatever and spit it out as a PNG or JPEG, basically high resolution screenshot. So if you're working in some format where it doesn't appear nicely in the LaTeX or text or anything, you can render it as whatever and have it automatically spit out an image and just embed the image. So a lot of flexibility and power. So again, load it up, library, Model Summary. The key function in Model Summary is just mSummary or Model Summary. These are the exact same function. This just generates summaries of summary tables of models. Then once you've run Model Summary, you can specify which output type you want to work in, for instance, cable extra, flex table, or GT, and then just tag on GT, flex table, or cable extra syntax afterwards and modify it as if you'd originally created it using one of those packages. Okay, so here's an example using model summary. And something I noticed is something changed in a recent version of my slides. There's these little artifacts here, these boxes. They only appear in these slides. They don't appear if I render them in RStudio, so I have no idea what's causing this little box to appear. I spent like 10 minutes trying to get rid of it. I just quit because I don't care. Anyway, so like Pander, mSummary just takes a model as an object and immediately spits out a table. So if I say run a linear model that looks like this, make it model 1, and I run model summary on mod 1, okay, it's just going to produce a table that looks kind of like a Pander table, except it's vertical instead of horizontal. So it says you ran a model summary on model 1. It has an intercept, which is this value. This is its standard error. The weight variable, this coefficient estimate, this standard error, then observations R squared adjusted, AIC, BIC, a log likelihood, and an F stat. Okay, looks a lot like that Pander table. It's just a markdown table. Okay, the thing is with model summary though, is model summary allows you to give multiple models as arguments to it, and it will put multiple models in the same table and figure out how to stitch them together. So what I do here is I say, I'm going to run model 1, I'm going to run model 2, and I'm going to run model 3. I'm going to put all these models into a list. And an important part here is I've named them. The names you give them in the list is what's going to show up at the top of the table. And then I just say model summary of this list of models. So what this lets you do is produce that really common style of table you've probably seen in a lot of empirical articles, where somebody has some favorite model they believe is the best model in the world and is the correct one, which they name model 3, and then they selectively remove things, making slightly stupider models back to try and prove their point that this is the best model in the world. This is a bad practice and people should stop doing it because it's almost, I mean, it's completely ridiculous from like a causal inference standpoint. If this is the properly specified model, you're essentially saying, oh, all these bad models, what's the point, right? Anyway, you can make that style of paper if your co-authors or advisor or your bad journal decides that you should lay it out this way. You can just give all of these models to model summary, and you can generate those sort of stepping up ones that artificially make it look like you're a genius by having come up with the greatest model in the world because all these other ones are bad. Okay? So some flexibility and some power. You can give an arbitrarily large number of models to model summary. You could give it a dozen models and it will just keep getting wider and wider. Okay. Next. So model summary, like I said, can produce lots of different output types. So for instance, if I say run a model summary on that model list from before, but I specify my output to be LaTeX, it's going to automatically send the output of model summary to Cable Extra and use Cable Extra, which is a really good package for generating LaTeX output, to generate a PDF output. That table, this is the exact same table here as on the prior. This is the markdown version. This is the LaTeX version of that table. Looks a little bit nicer just due to the way LaTeX typesets things. So this looks like you'd see in like, a lot of journals that LaTeX typeset things. So if you want to customize model summary output, it has a ton of flexibility and also, like I said, can use Cable Extra, GT, and Flex Table to modify how it looks. I say go straight to its documentation. It has good documentation and a lot of it. If you want to tweak things, it's not the kind of thing you memorize how to work with it. You just go and look stuff up. Okay. So if you want to save a model summary and produce a file out of it, you can say model summary, the thing you want to get a summary of, and then specify the output is a file path. If I say here, I want to produce xtable.png, model summary figures out what I want it to produce. So it's going to go get this model list, make a summary table of it, and then it's going to export it as a ping image onto disk. If I specified PDF, it would export it as a PDF thing. If I specified RTF, it would make it into a text file. It can figure out how to generate all sorts of different outputs. And what it will do is based on the output you provide it, it will go and use a different table making package to generate the table. Very powerful, very flexible, pretty easy to use. Okay, here's an example of taking a model summary object and adding something to it using GT. So if you say, run a model summary on model list and specify the output is GT, the resulting thing from this will be a GT object. If it's a GT object, I can pipe it into GT commands to make edits. So now I say, take my model summary output and then add a header where my title is table 1 linear models and my subtitle is DV miles per gallon. It's the exact same table as before, but now it's got a title and a subtitle like I added to the Star Wars table earlier. Okay, so again, GT's support for PDFs is kind of immature, but the GT output is really good for making HTML output or image output. So if you're going to be working in HTML doc, I really like how GT works. If you're going to be working in PDFs and you want LaTeX, I recommend either Cable Extra or Flex Table. If you're going to work in Word, just go straight to Flex Table. Kind of sucks needing to learn syntax across lots of different packages, but you know, whatever. Honestly, you could probably get by entirely in Flex Table across all those formats if you needed to. I just really like certain GT features. Okay. So another package I want to talk about is GT Summary. GT Summary is similar to Model Summary in that it takes advantage of Broom, GT, and Cable Extra to make a flexible table making framework. The thing with GT Summary is what I use it for anywhere. The thing I use GT Summary for is making descriptive statistic tables for data frames. GT Summary can take model inputs and make model tables, but I don't like the style of its model tables as much as model summaries. So I'm going to show it for descriptive statistics here, though you could theoretically use GT Summary for everything. Okay, so here's an example. So by default, GT summary tables, which are created with the table summary function, they provide a lot of information. If I say take the MT cars data set, select only its first 9 variables, and then do table summary, I get a table like this. It says characteristic. Characteristic is the column name. I would prefer it say columns or something, but it's characteristic. I think the people who make GT summary are in biology or some biosciences field, and so they kind of use the setup and terminology of people in the biosciences. Anyway, so it says characteristic, and then these are the variables. Miles per gallon, which has I believe this is the median value. These are quantiles. So this is the median, the 25th percent quantile, and the 75% quantile. Then for cylinder, 4, 6, and 8, these are frequencies. There are 11 observations of 4 cylinders, 7 of 6, 14 of 8, which comprise 44% of the entire data set. And then for other continuous variables, again, it's the median and quantiles of different types. Okay. For binary variables, it just says the number that have a value of 1, right? Or whatever is the non-reference category. Okay. Also provides a sample size up here, and it also specifies here that what's being displayed is the median in an interquartile range or the n in percentage. So this is all the default settings. You can configure all these things to display whatever you want, but this is what it does by default. And this is actually a pretty nice sort of set of summary statistics. You know, I might prefer something like the mean instead of the median, and maybe different quantiles than this, but it's not bad. Okay, so cool thing about table summary. Table summary has all sorts of functionality to do things like breaking it into multiple tables. So here I say MT cars, still the first 9 columns, and then table summary, but now I say I'd like it tabulated by values of AM. So what this does now is my table now has 2 columns. This is all the data where the AM variable takes a value of 0. This is all the data where AM takes a value of 1. So this is descriptive table stratified by some variable. So you can see there's 19 observations here, 13 here, all the descriptive statistics. This is pretty handy. This lets you kind of quickly create certain common types of descriptive statistics tables. This is the kind of thing you might do if, for instance, you have like a control population or a control sample and a treatment sample, and you wanted to show people that they're basically the same, that there aren't any major differences between treatment and control group, you'd stratify in the treatment and then show all the relevant variables, and hopefully they'd be really similar across the two sides of the table. Very easy to do in GT summary. Okay, so with GT summary, like with model summary before, I can pipe it into GT functions to do GT operations to it. So here I say again, I'm going to create my table summary from the last slide, stratified by values of AM, but then I say, and then make it a GT object. This is the syntax for GT summary to convert it to a different table making package's syntax. It has its own function as GT. There's also an as cable extra. And then I'd say, well, tab spanner. I'm going to add label transmission across all columns that start with the text stat underscore. This is a way to make a spanner across the two statistic columns inside GT summary. Turns out under the hood, they're named stat underscore something. So it adds this spanner transmission and then a horizontal bar across it. And then I add a tab header using standard GT syntax for motor trend cars descriptive statistics. So dressed up a table a little bit using some GT syntax. It's the same table as before, but now it looks a little bit nicer. Okay. So one little bonus I insert here. So here's a question. How do you add the superscript and note in the table? I didn't. It was done automatically by GT summary. So it has options. In fact, GT and the other packages have all sorts of options to add footnotes, subscripts, to add little numbers in here that link to other things. All these packages can do that with their own little syntax, but GT summary just does it automatically. If you changed what the values were in the table here, it would also update this down here too. Yeah, if you look in the documentations, these packages often have a lot of really cool functionality. Anyway, here's a bonus here. It's a totally unnecessary bonus that has nothing to do with what I've shown before, but this is one of my favorite little packages. Oh, how do you add more footnotes? It depends which table making package you're working with. If you're working in GT, I think it's tab footer, and then you can specify where you want the footnotes to refer to in what cell, and then it can add a footnote. I don't do footnotes too much, so I'd have to look up the documentation myself, but I assure you it's not hard to do. Okay, next one. So this is a really handy package. This package is CorePlot. CorePlot is a package that does one thing, and it does it really well. What it does is it generates correlograms. Correlograms are essentially a visualization of a correlation matrix. It makes it a lot easier to look at a matrix of correlations between variables in a data set than a conventional table. All you have to do with CorePlot is load up CorePlot, and then say, run CorePlot on some correlation matrix. So in this case, I've said, run a correlation on all the variables in MT cars. This produces an actual correlation table. But then I've run CorePlot on that thing and added a few options here to make it look nice. Okay, this is what it looks like. This is a correlation plot of every variable in the MT cars data set. Where's there should be ones up top. Did I accidentally remove the ones up top? Weird. Anyway, there should not be ones up top. Okay, so the way this works here, for instance, is this cell right here is the correlation between the weight variable and the AM variable. So negative 0.58 would be its correlation. And the way this works is that the circles get redder, bigger, and darker when the correlation is negative and stronger. They get bigger, bluer, and the number gets more positive. When the correlation is more positive, it has sort of a scale over here. So my advisor is an old structural equation modeling guy. He likes to see the correlation matrix for literally anything I'm doing before he trusts the things that I'm doing. So what I do is I provide him correlograms like this so he can really quickly look at the correlations between every variable in a data set. It really draws your eye to things when there is or is not a correlation between things. This is a fantastic package for visualizing correlations. I use it all the time to take quick looks at my data set to see how things are related to each other. Okay, so I just wanted to show it to you because it's one of my favorites. It's a tiny little package. It's pretty basic, but man, it is useful. I use it all the time. Okay. So that's all I've got on model results. Does anybody have any questions on the model results stuff before I start ranting about reproducible research in the last 25 minutes? Okay, and if you do have any questions, hit it up and I'll pause and I'll go back, but I'll keep chugging on. Okay. So now I'm going to talk to you about one of my favorite things to talk about. So let's talk about reproducible research. So why and what is reproducibility? So I guess why is reproducibility? Doesn't make any sense, but why reproducibility and what is it? So reproducibility is not replication. So if you've heard people talk about replicating a study or something, replication is when you run a new study, you write a new paper to show if and how the results of some prior study hold or do not hold, very often with new data and some new population or something like that. You're basically rerunning the same thing more or less in a similar way, but with new data or methods. Reproducibility is about rerunning the exact same study with the same data and the same methods and getting the same results. Okay? So, reproducible studies that can be reproduced, can still be wrong. Reproducibility doesn't tell you anything about if it would work again in some new population or something. Reproducibility, in fact, makes it much easier for other people to prove that your study is wrong, because reproducibility is about making it so other people can rerun everything you did and get the same results. Hopefully get the same results anyway, right? Okay, so what reproducibility means transparent research practices. If your work is reproducible, other people can see literally everything you did and thus get the exact same results from the raw data. Nothing is hidden from them, which is good for science. It means minimal barriers to verifying your results. Good, well put together, reproducible research is basically push button. Somebody should be able to download a GitHub repository of your journal article, press one button, and get the exact results that are shown in the journal article. That's good reproducible research. Okay, so something I'd like to drive home. Any study that is not reproducible can be trusted only on faith. Okay, I'll repeat that. Any study which is not reproducible is only trustable based on faith. If somebody writes a journal article, no matter the prestige of this person or whatever, and their work cannot be reproduced because they don't share the code, they don't share the analysis and everything, they're asking you to trust them that they did everything right and they are not lying to you and they have made no mistakes. Okay, so if you think about it this way, this means that is obviously a bad thing. Science is not about just fundamentally assuming everyone did everything literally perfectly. But basically, nearly every journal article that you encounter, especially written more than 5 or 10 years ago, is exactly this. There's no documentation, there's no code, you can't reproduce these things, you just have to assume they did things correctly. This is bad for science, and I wish people would stop doing this. And a lot of journals, in fact, are now making it so if your work is not reproducible, they will not accept your paper. You have to submit all the code and everything necessary to reproduce your results, or they won't accept your submission. Okay, so definitions of reproducibility. Reproducibility comes in sort of 3 basic forms. The first is empirical reproducibility. This is reproducibility in like data collection, that being the actual procedures used to generate the data. If you did it exactly the same way, you'd get exactly the same result. The next is statistical reproducibility. Statistical reproducibility means your results would be reproduced using alternate methods of inference, but on the exact same data than the same thing. So statistical reproducibility means I would get the same result if I sort of I'm not changing like the variables or changing the data, but rather I just change the estimator or something like that. I would be able to reproduce it, supposing it's the correct estimator. The last form of reproducibility is computational reproducibility. This is reproducibility in the cleaning, organizing, and presenting of your data and your results. So computational reproducibility is all the things that happen from when your data file is opened and you start like creating and modifying variables to running the models and spitting them out into your tables and your plots. Okay, all the stuff you basically do in like R. So R, as I've been showing you all term long, is really well suited to enabling computational reproducibility. Python is also very good at it. Julia is pretty good at it. Other languages are good at computational reproducibility. So you probably, if you think about it for a minute, you maybe realize that every homework assignment you've done in this class is a piece of reproducible research. All of your markdown documents, provided the raw data, can regenerate the results that you get by pressing a single button. Okay, that is as difficult as reproducible research need be. You've been doing it the entire term. It's not difficult to do. You already have some framework to do it, which is an R markdown document. When I say R is well suited to it, I've been making you do reproducible research this entire term without actually really calling it that most of the time. Turns out it's pretty easy to do. And in many ways, it's easier than doing it the bad way, which is copying and pasting shit into Word and handing it into homeworks and stuff, right? Okay, R markdown docs are great. Anyway, the thing about computational reproducibility is computational reproducibility will not fix flawed research designs. It will also not remedy improper application of bad statistical methods, okay? So these things, research design and learning stats, are very difficult, non-automatable things that you want to develop skills in. Those are the important things you want to do. Computational reproducibility is something you want to automate as much as possible. You should make it so you don't have to think about it. You should just be following practices that automatically result in computational reproducible things, so that instead you can focus on doing a good job with your research design and a good job with your statistical design. These are the hard things you want skills in. Computational reproducibility is in large part learning how to spend less time doing these things. So let's talk about computational reproducibility, the thing that R is actually good for. Computational reproducibility has a few different elements. The first element is shared data. Obviously, people cannot reproduce your work if they do not have your data. Researchers need your original data to verify and replicate your work. If you're in the social sciences like me, often you can't really provide people with your raw data because it's restricted access data. But what you can do is make it so that your project can be downloaded. And if they get access to that restricted access data, all they have to do is throw the file into one labeled folder in your document and then knit a document, and it will grab the data appropriately from that and do all your analyses and put out the results. And try and keep the barriers as minimal as possible. When possible, though, share your data. Hoarding data is not a good look. Okay. The next thing you need is shared code. You have to give people all the necessary code to run your entire project so that you can make all the decisions that you made in that project transparent. You want it so that people can see everything you did. All the choices you made should be laid bare, and that's what code does. If you give people code that starts with the raw data and it finishes with the analysis, they can see everything you did. If you made some gross mistake, maybe they can find it. But, it will in general reassure people that you are doing, like, you're not doing something like misleading them on purpose, because they can see the code and they know that they could dig around and find something done improperly if they look hard enough. Next is documentation. So if people have your data and they have your code, but your code looks heinous and they don't know how anything works, it's not the most useful thing in the world. So another thing you need is documentation. Your code should be, in a reproducible project, your code should be either self-documenting, which is usually a myth, but sometimes what's happening is so obvious that it documents itself, or you have written descriptions to make clear what's going on. These things kind of can blend together if you have, for instance, like a markdown document with text describing what's happening in each chunk, or you have big comments inside the actual syntax file. I tend to have lots of comments inside my syntax files. Okay. Lastly, The last thing, the element of reproducibility, this one is not technically necessary, but it's highly recommended, is version control. Version control, which is things like Git and GitHub, is a way of documenting the entire research process, every change ever made to any file in your entire project. Version control prevents losing work because everything is backed up every time you make any kind of a change, and you can revert every change that was ever made. And it also facilitates sharing things. It creates a public repository that multiple people can collaborate on, merge their code, download stuff, make changes, all of that. I highly recommend engaging in version control. It's sort of the best way to make reproducible projects. And in fact, nearly every, for instance, R package has a GitHub repo for it. I like the idea of making your journal articles a GitHub repository. So if people want to replicate them, they just pull down all your code as a repo. My dissertation is a GitHub repository. Okay. So within all of that, there are multiple levels of reproducibility for research projects. So for academic papers, the degrees of reproducibility vary. The old school common one was, well, just read the article. Everything's in there. That is never true, but it's a really common response, and was a really common response, many years ago. For if you say, I want to reproduce your work, they'd be like, well, everything's in the article. It's obvious. No, it's not. Usually there's all sorts of hidden things, but that's what they'll do. The next is some shared data with documentation, which should be the absolute bare minimum that anyone does for a journal article. They should at least share the data and have some documentation on it, exactly what was done. This still sucks because you won't be able to detect if they made mistakes in their code, but it's at least a start. The next one is shared data and all code necessary to run the analyses, do all the data cleaning and everything. This is sort of the basic ideal, right? If you're going to produce a journal article or something, you should do this, right? At least have your code available and the data, if possible, shared, or tell people exactly how to get the exact version of the data file that you have. Above this, we start to get things like interactive documents. An interactive document is something like an R Markdown document. The interactive document takes the raw data, which you have shared, and runs all the code and produces the analysis and all the text and everything like that in one go. So this is a push button solution to reproducibility. If your R Markdown document knits for you and your directory structures are set up properly, you can hand it to somebody else and it will knit for them and they'll get the exact same results. That's good reproducibility. But you can go further than this. You can go into research compendiums or research compendia. A research compendium, I think I'm going to talk about in a little bit, is basically a fully contained standardized version of an interactive document where everything is packaged up like an R package. The next step above that is something like a Docker compendium. A Docker compendium or a Docker file is basically a self-contained computational environment. The Docker thing would actually, for instance, bundle the copy of R and all its packages used to knit the document. So if somebody opens it up 15 years from now, they're using the proper versions of everything to reproduce your work. A little bit more extreme, but a lot of people do this. Okay. So interactive documents. Interactive documents like our Markdown docs, right? They combine some code and text together into a self-contained document. You've been using them all term. They're fantastic for this, right? Your Markdown document would load and process your data, run your models, generate your tables and plots in line with text, and ideally in-text values will also automatically be filled in. Everything is sort of obvious and fully documented. Interactive documents are great, right? They allow your readers to examine the computational methods you used within the context of the document itself. Thus, they're sort of self-documenting. Everything that was done, you can see in one place. By rerunning the code, of course, they also reproduce your results on demand. If they have your data, they ought to be able to press one button and spit out your entire journal article. I don't usually go so far as to be able to spit the entire journal article out like this, but I usually at least make it spit out all the tables, the plots, and everything like that. Okay. So common platforms for this are Markdown, obviously. We've been using it all term. In Python, there's Jupyter Notebooks and some things derived from Jupyter Notebooks that are good for doing this sort of thing. Actually, I forget what the Julia ones are called, but they're out there too. Okay. Next thing is research compendia. So a research compendium is a portable, reproducible distribution of an article or a project. It's the next step above an interactive doc. So these things feature an interactive document as their foundation. But then on top of it, they add files organized in some recognizable structure, like the structure of an R package. They'll have clear separation of data, methods, and output. The data will be read-only, sort of a common practice here. And then they'll have a well-documented or even preserved computational environment. So they'll at least say what packages in R were used to do everything. Even better, they'll be wrapped in a Docker container. I don't usually go so far as to wrap things in a Docker container, but I have friends who do. Okay, so if you want to do this, RR Tools by Ben Marwick over in Archaeology, who's one of my committee members of my dissertation, he provides a simplified workflow to do this in R. I do have a compendium of my own posted up as sort of an example on my GitHub. Okay, another thing to know about is Bookdown. Bookdown, which is also integrated into RR Tools, but it's sort of a broader framework for this, Bookdown can generate documents in the proper format for articles, theses, books, or dissertations as are markdown documents. So what Bookdown does is it provides an accessible alternative to things like writing LaTeX for doing typesetting of a book and doing reference management. You can do it all in Bookdown instead of messing with those BibTeX files and LaTeX templates. You can also integrate citations and automate reference page generation using BibTeX files that are, for instance, produced by Zotero. So you don't mess with them, you just have Zotero link into it and get all your citations, and you don't have to mess with the stuff manually. Bookdown can support HTML output to make like websites and stuff, but it can also render PDF documents through LaTeX to make publication-ready books and documents. If you've seen the R for Data Science book, that is a Bookdown website, and that website's code that generates the website, if they flick it to PDF output, produces the actual printed book you can go buy at a bookstore. Okay, those are Bookdown documents. They can produce anything you want, but they're from a Markdown doc instead of anything else, right? Okay. For University of Washington theses and dissertations, Ben Marwick has a package called HuskyDown, which uses our Markdown, but it renders the documents via UW's approved LaTeX template to get perfectly formatted UW dissertations and theses. This is a nice way if you want to make your dissertation or thesis a Markdown document, but have it look UW style, you can use this package. Okay, so running low on time, I'm going to keep chugging along. Next thing I want to talk about is best practices for organization and portability of your projects. So, organizing research projects is something you either do accidentally and typically very badly, or you do purposefully with a tiny bit of upfront labor, which makes your life a lot easier later. Uniform organization in your projects, that is making every project have basically the same organization, makes switching between them and revisiting them a lot easier over the long term. I recommend that you structure your projects something like this. You can do whatever you want, but some vague thing like this. I have a top-level project folder named whatever the project is. Inside of there will be like a README file, a data folder containing derived, that's data created by my scripts, and raw read-only data, the original data for the project, documents like the paper that you'd be writing the journal article, and then syntax, which would contain all the functions and models you're running, possibly with a bunch of subfolders if you have a lot of .r files. The idea here is there's a really clear hierarchy. You know all written content is in docs, all code is in syntax, all data is in data. The naming is uniform, everything is lowercase, my words are separated by underscores, and the names of everything are self-descriptive. I have no questions about what anything in this entire hierarchy is. I can glance at it and know exactly what there is in everything. If you structure every single one of your projects the same way like this, it makes it really quickly to jump between them and find everything you need. Okay. So, next thing, workflow versus projects. To summarize the great Jenny Bryan, you should separate your workflow from your projects. Your workflow is stuff like the software you use to write your code, like RStudio, the location you store your projects, the specific computer you use, and any code you ran earlier or typed into your console. These things should be set aside on one side of your life. The other side should be the actual project. These are the raw data, the code that operates on your raw data, the packages you use, and the output files or documents. Nothing over here should rely on anything over here. Okay, so to make this work, Your projects should not modify anything outside of that specific project, nor should they need to be modified by someone else or future you to run should they be moved somewhere else or something like that. Your project should be fully independent of your workflow. Everything here should operate no matter how these things over here change. If you move to different software, it should all work. If you change the location it's stored, it should all work. If you move to a different computer, it should all work. And if you had a bunch of code typed into your console or not typed into your console, this shit should all work exactly the same regardless of that. Any violation of this makes your research non-reproducible. So follow these sorts of guidelines. Okay, so to make this work, to make your research fully reproducible, your research must be what is called portable. Portable software operates fully independently of your workflow, including fixed file locations on your computer. If you want something to be portable, you must not do any of these things. Never use set working directory in your scripts or RMD files. Always use absolute paths. Absolute paths refer to your project directory and directories below that one, except for fixed immovable data sources like secure data on an external hard drive you plug into your computer. Okay? Never use install.packages in a script or RMD files, and never use rm list equals ls anywhere but in your console. A script should never contain that. None of these things should ever be in your scripts or RMD files at all, unless necessary for fixed immovable data sources. What you should do is use RStudio project management features or the here package, which is a package that does the same thing, to set your directories. Use relative paths. Do things like read CSV, my data folder, mydata.csv. This is relative to the top level of your project. Load all required packages using library and any scripts that need them, and make it so RStudio never saves your workspace. Every time you close RStudio, it should delete everything present in it, and you should start fresh every time you open it. To do that, go to Tools, Global Options, look at Save Workspace, and set it to never. Okay? Do all of these things and none of these things. Okay, so often you don't want to include all the code for a project in a single RMD file. Reasons for this are the code is going to take too long to knit. Maybe you got some big Bayesian models or something like that. They take forever. You're working with big data. It takes too long to knit. Another thing is it ends up being so long it's difficult to read. I don't like RMD files to get super big unless they're slides where I have no choice. You might want to break it out into multiple files. That is, you might want to divide and conquer. So there's two ways to deal with this. One way is to use separate .r scripts or RMD files, which when run, save their results from, say, the complicated parts of the project. And then you load those results. Instead of running the R scripts again, you just load the results in the main RMD file. This is good if you're loading and cleaning large data sets. It's also good for running slow models. You run the model and you just reference its output instead of rerunning it every time you knit a document. Another thing you can do is you can use the source function to run external R scripts when the RMD knits. This is good if you have a big file that doesn't take a lot of time but has a lot of code in it. You can call out to that file and run it when you knit the document, but you don't have to put all that code in your RMD. This is also good for loading project-specific functions. I very often have some external file with a bunch of functions I'm going to use in it, but I don't want them in my RMD because they take up too much space. Okay. Most of my projects are structured like this with lots and lots of .r scripts that are external and then one RMD that puts everything together. Okay. So I find it beneficial to break your project into many, many files, lots of files all over the place. So I do this by creating lots of files that have things like scripts containing specialized functions, scripts that load and clean each set of variables, scripts that run each set of models, scripts that make each set of tables, scripts that make each set of plots. And then with all those, a single main RMD that runs some or all of these in the background to reproduce the entire project. So all the little functionality is up in separate script files, and then one RMD which has little or no code in it, except calling out to those other files. Okay, splitting up your project carries some serious benefits. Once a portion of your project is done and it's in its own file, it is totally out of your way. You never need to go back and look at it unless you need to correct some error. right? There's no reason to browse through a file with 10,000 lines of code in it if you're ever only working on like 50 of them at a time. Put it in its own file. If you need to make changes, you don't have to search through some huge file. You just go to that little modular file that does that task, you fix it, you save it, then you put it out of your way. This also means entire sections of your project can be added or removed quickly. You might be able to convert them to an appendix or something just by moving those modules around in your document. And importantly, a big one as you move further on into sort of reproducibility, many files is the only way to build a proper pipeline for a project like an adult software developer. So, what's a pipeline? Professional researchers and teams design their projects and software as what is called a pipeline. A pipeline is a series of consecutive processing elements. These are things like scripts and functions in R. At each stage of the pipeline, there will be a clearly defined input and a clearly defined output for that stage. The pipelines do not modify their inputs in any way, and they produce the exact same output every time they are rerun. So they're little modules that do one task. They take in the same kind of thing, and they spit out a different kind of thing, but it's always the same thing taken in. It's always the same type of thing coming out. Okay? So what this means in a pipeline is if you modify one stage of the pipeline, you only need to rerun the subsequent stages. They don't modify anything earlier in the process. So if you modify something, you only got to rerun the later stuff. This also means different people can work on each stage at the same time. They're all isolated. So long as the general type of input and output don't change, people can modify the internal code to their heart's content. This also means problems are fully isolated within one stage. If something is going wrong, it must necessarily be a problem only in one stage because the code is fully isolated. A nice thing, if you've designed your entire project as a pipeline, you can now depict your entire project as something called a directed graph of dependencies. Turns out you can visualize projects. Pipelines look like this. In a pipeline, in this example here, every stage of the project is an oval. At the stages, they take some unambiguous input and they produce some unambiguous output. Everything that precedes, that is going backwards down the errors, everything that precedes a given stage is a dependency, something required to run that stage. Everything after that depends on that stage. In this example, this thing takes 2 CSV files in, it loads the data. It spits out a full data RData file. This RData file gets sent to 2 separate scripts. One of them reshapes the data, the other one runs descriptives. The reshaped data produces this model data here, which goes into some models. The models then produce a table and some plots. The descriptives go in here and produce a descriptive table. And then the table, the plots, and this table all go into a paper RMD, which spits out a PDF of the paper. Okay? This is an entire research pipeline. So if you want to automate this process, there is an R package called Targets for building fully automated pipelines that does things like detect where changes were made and only run the necessary components of your project again to update according to the changes you made. Targets is great for this. The older package for this was called Drake. And I know people may have to jet. It's 5:22 and I'm a little bit behind. That's perfectly fine. Hope you had a great turn. But if you stick on for another 5 or 10 minutes, I'll wrap up. Okay, or maybe you're watching by video. That's cool too. Last thing I want to talk about here before we do wrap up is some tools, which is opinionated advice. Okay, on formats, I say that you should avoid closed source or commercial software and file formats except where absolutely necessary. Use open source software whenever possible. So, open source software and file formats are fantastic for a number of reasons. Open source software is always better for science. It is my firm belief, and I think you should agree with this in general, that people should be able to explore your research and reproduce it, replicate it without buying commercial software. Making people pay hundreds or thousands of dollars for a software license just to be able to replicate your science, which was probably publicly funded, doesn't seem very good. You don't want your research also to be inaccessible when software gets updated or software gets discontinued and is no longer available. Okay? Next, it's often just better. Open source software is typically updated more quickly than closed source software. It tends to be more secure because you got a million people probing at the code looking for problems, and it rarely gets abandoned. Some of the most popular open source software was started being written in the 70s or 80s. It is still alive today. People who maintain open source software don't care about making money on it. They just maintain the things that they use. So popular, useful things tend to last forever. Open source software is in general great. R is open source software. Okay. So ideally also I say use software that reads and writes purely raw text. Raw text lives forever. It always sort of works. There's no mysteries about it. You can open up a raw text file written in the 1960s off of a tape drive tape, and it will still work today. Okay, so about text. Some advice. Writing and formatting documents are two separate jobs. They used to really truly be two separate jobs back when you had writers and editors and the internet hadn't blended these things together. Okay? Because these are two separate jobs, you should do them separately. Write your documents first and format them later. This is the point of Markdown. Markdown is about ignoring the formatting and focusing on the writing and letting the computer format the stuff for you when you need it. Word processors, like Microsoft Word, try to do both the writing and the formatting at the same time. They usually do it badly, and they make you waste lots of time by leading you to do formatting instead of writing. Word is the ultimate device for procrastination by allowing you to do things like tweak your fonts, your paragraph size, the arrangement of things, messing with your table of contents, all of that junk. All those things should be generated automatically or by a professional, so you should stop messing with them. It's okay to use Word. Just stop doing that other stuff and use it just to write. Okay, I recommend finding a good modular text editor and learning how to use it. Atom is what I use. I like Atom. I do almost all my writing in Atom. I actually don't write the main text of my papers in Atom. I still use Word because I can't seem to break away from it, but I do everything else in Atom. Sublime is a good commercial text editor. There's also things like Emacs and Vim. I don't recommend getting into those, but if you're into them already, stick with it. They're great. Okay, last thing I want to talk about, I guess I thought it was that, but now it's version control. Version control is an idea that originates in collaborative software development. The idea behind version control is that every change ever made to a piece of software is documented, saved automatically, and fully revertible. Version control allows every decision ever made in a research project to be documented automatically so people can go back and see what you did. Version control can do all these things. It can protect your work from destructive changes. So if you made some sort of error, you don't overwrite stuff, you can revert that change. It simplifies collaboration by allowing you to merge changes by multiple people simultaneously. It lets you document design decisions by sort of building all this into one big structure. And it makes your research process transparent because everything you ever did is visible on the entire chain of changes in your version control. Okay. So Git is the dominant platform for doing this, for doing version control. And GitHub is a free and now Microsoft-owned platform for hosting Git repositories. You don't have to host them on GitHub, but it's a convenient place to do it. Repositories are just folders on your computer. And in these folders, every change you ever do to any files gets tracked by Git software. Once you get satisfied with changes, so if you make a bunch of changes to some files in that repository, you just commit them and push them to a remote repository that stores your project. You can do this with a command line interface, or you can do them with something like this right here is my graphical user interface for Git for pushing changes, for instance, to this class. If I made some edits, I would just say, I could like fetch the current status of the repository. I could make changes here, commit them and push them, and then the website would update, including these slides. Okay. So you manually sort of commit and push things whenever you make enough changes to be worth it. Others can copy your project called pulling. They can pull it down. And if you permit, they can also make suggestion for changes or just push their own changes to it. So it makes it easy to collaborate. Constantly committing and pulling changes automatically generates a running history of the project that will document its full sort of evolution. Every change ever made will be documented by these different commits you've made to the repository. So you can see everything that was done. If you look at the GitHub repo for this class, you can see every change I ever made to any slide or whatever in the class's history. Git is already integrated into RStudio under the Tools menu. It requires a little bit of setup, but there's a little pane in the top right in RStudio you can use. It's integrated already into RStudio. Why not check it out? One nice thing about Git and GitHub is that GitHub also serves as a sort of curriculum vitae for the programmer. So by archiving all of your projects up on GitHub and making them publicly viewable, people can see that you're competent in programming and research. All your repositories are up there. They can browse through and see your code. They can see all the things that you've done. If you're planning on working in the private sector, an active GitHub profile will give you a leg up on the competition, or at least make you even, because basically everybody applying for a technical job is going to have a GitHub profile too. If you don't have somewhere where people can see the work you do in the code, you're probably actually going to be lagging behind. If you're aiming for academia, a GitHub account signals technical competence and also an interest in research transparency if you put your research up on it. It's like, I'm into reproducible research, I'm into transparency, everything is up there so you can see it, browse through my code, I hide nothing. People like this, especially in more technical departments. Okay, sorry for going over, let's wrap up really quick. So what have we learned in this class, or in theory, what has the fire hose exposed you to? A lot of different things. You've learned how to get data into R from a variety of different formats. You've learned how to do a little bit of data custodian work to manipulate and clean data. I've shown you how to make pretty visualizations in ggplot, how to automate things with loops and functions and apply statements. I've shown you how to combine text calculations, plots, and things into dynamic R Markdown reports to do some reproducible research. I've also shown you some random things like how to acquire and work with spatial data, some fun stuff, right? So what comes next? So now that you've gotten this background from this class, you're hopefully a little bit better prepared for doing other things like statistical inference classes. That is, more classes from CSSS. These classes will teach you about functions for hypothesis testing, doing hierarchical mixed effects models, all sorts of different things, machine learning, survey design. All that stuff is a lot easier and more straightforward to use if your data are already clean and organized nicely. And the things you've learned in this class taught you a little bit of how to work with structures that might be produced by functions you learned in that class, like regression models, using things like Broom and ggeffects from today. Things I recommend you do: you will lose all of this knowledge if you do not keep at it and practice at least periodically. Okay, I recommend, if you don't have anything else cooking, replicate analyses you've already done in other software like Excel, SPSS, or Stata. Do it up in R just to kind of keep yourself sharp. Think about using like dplyr verbs, tidy data principles for data. Just sort of mull using those things when you encounter data or when you see data. Later, go back and apply those things. Maybe also use R Markdown for reproducibility. Maybe just make a lot of your papers and documents in R Markdown, even if they don't have embedded code. Just get used to using it constantly so that you don't lose these skills. Other things you might look into are things like picking up version control in RStudio, maybe making interactive apps, write your own functions, make your own packages, stuff like that. Anything to keep your skills sharp. Just keep at it, and these skills will sort of build up. Some course plugs. Okay, so these are some course recommendations depending on your background. If you've got no stats background and if you want it, I recommend starting at like SOC 504 Applied Social Statistics. If you finish like SOC 506, I recommend Maximum Likelihood by like Chris Adolph, CSSS510. If you want to get more into visualization, he also teaches a visualization class called Visualizing Data. There's also a really good one in computer science that's quite good but hard to get into. If you study events or duration data, event history analysis is great. And it's also a good introduction to maximum likelihood. If you work with network data, I don't know how often this one is offered, but social network analysis is pretty good. If you work with spatial data, I've already plugged this one. If you work with time series data, there's kind of two different time series and panel data classes. They're both good. I like them both. They kind of cover different things. So a lot of different classes you could take out there. And if you ever have questions about sort of class to take or something, shoot me an email. I've taken most of the CSSS classes. I'm pretty familiar with. Okay. Sorry for going over. That's all I got. Thank you, all of you, for being the last class of people I will teach at the University of Washington. As I am graduating next week, I am done. This is the last time I will ever teach this class, at least here at the UW, probably. So thank you all for being a fantastic class. I hope you got a lot out of it. Do feel free to still reach out to me if you got questions in the future. Oh, what's next for me? I have a postdoc at Oxford. So I am going to the Center for Social Investigation at Nuffield College, Oxford, to go and work for David Kirk, who's one of a major sociologists, very esteemed, and Robert Sampson on a project on gun violence. So I'm doing that, and I'm super excited about it, and also afraid because I have to leave behind all the United States and sell my car and all my worldly possessions and things. But it's going to be a pretty cool adventure. So that's what I'm doing. But anyway, this is the 9th and final term of teaching this class. So it's been a blast, and I'm glad I had a good batch of folks. I hope great success for everyone else in the future. I hope you stick with it, and if you don't, I understand. If you're daunted by this and you find it really hard, that's normal and fine. We all started awful at coding, and most of us also learned pretty slowly. The trick is keeping at it. Very few people actually have a natural aptitude for this stuff. Normally, you just got to kind of keep grinding at it. Please do. I think it will be generally beneficial to your career to sort of develop these skills. It will be a slog, but in the long run, you'll probably enjoy it. So that's all I got for you. It's been a good term. Hit me with email and Slack if you got questions.
Thank you.
Absolutely. Absolutely. I got nowhere else to be.
Hey there. Well, thank you so much. This was an incredible course. I'm super lucky to have caught you before you left. And congrats again. That's super exciting. I have 3 quick questions. One that I've had for like the entire quarter, and 2 that kind of came up today. One that you touched on just towards the end of class around GitHub. Would it have been good practice to like for each of these homeworks for us to like set up our own repository and base our homeworks out of that, or?
It could, and in fact, a lot of people actually, there's other classes on campus where they do that, where they actually set up a GitHub repo and they submit it that way. It's actually the CSE 580 or 560, whatever that class is, does it that way. I just don't want to overwhelm people with it, but if this is like a 4-credit class or something, I'd probably seriously consider it, just because it's good to learn. GitHub it's so useful. It'd be worth it'd be worth doing just to like learn and get used to it. I mean, for instance, I mean, like for me, right?
Like I'm thinking about maybe starting to do that for future classes, just as like a exercise to practice it.
Yeah, I think it's a good idea. I basically almost anything of any real value, I hook up on my GitHub. You know, I don't have a huge number of repositories, but I tend to put things like, I even put like job talks, big presentations and stuff. I just kind of huck everything up here and have like a repo. And I just think it's a good way to handle everything. I put research projects up here too. Not all my papers, because some things just have so much restricted access stuff.
For sure.
Really bothered. But I think it's a good practice, and it's, you know, it's good to get into.
Yeah. Okay, cool. Second question was, very sad that you're leaving, very excited for Brianna to take over, but will these materials still be available? And it's just going to live there in eternity.
Yeah, they'll live there in eternity. I just probably won't be updating them, you know. Since I'm not teaching it, but I'm sure I'll probably end up teaching a similar class later, and so it's a new repo and page will show up later.
Gotcha.
Brian will be taking over his own version of it, I assume, probably just cloning this repository and then building on top of it.
Gotcha.
Cool.
And then the last question, which I've been meaning to ask the whole quarter, but was semi-afraid, but now that you brought up the reproducibility and free access, I thought it was especially relevant, you know, using open source software. I do a lot of work in Tableau. And A, was curious on your thoughts on it, and B, was curious if you've ever used it, because I know there are ways to like incorporate R into Tableau to do some more advanced analyses, but I've personally never done that. Now my cat is meowing. Sorry about that.
Yeah. I don't personally have almost any experience with Tableau at all. I'm pretty much a pure R user. I know that they can kind of talk to each other, and of course, what you can do is you can always just export things from R and open them up.
Right.
Tableau is actually useful, and if you're going to be anywhere in like the private sector and some government kind of
Yeah,
Tableau is really useful. And so it's one of those skills.
for sure.
What's really funny is I sort of have told people this who've asked me about like job applications. I'm like, I actually would not have a fantastic CV for a lot of these jobs because I'm basically purely like an academic R programmer. I
Right,
barely use SQL. I don't know anything about Tableau. I don't do any of that shit because it's like I'm in this like narrow area. But those sorts of
right,
skills are super valuable because that's what people are going to use in these environments.
right.
Yeah.
Okay,
So it's
cool.
worthwhile. It's worth knowing. It's just, Tableau, most people who I know who know Tableau well and are well find Tableau to be pretty limiting. But,
Really? Okay,
it's like, it depends what you need to do. If you're doing
for
sort of
sure.
basic sort of, if you're making kind of like dashboardy type stuff,
Exactly.
I know that, for instance, my contact at the Seattle Police Department, they do so much of their data stuff through Tableau, and he's a quite sophisticated user, and he likes Tableau for that. So in
Hmm.
some kind of like administrative environments and stuff like that, it's like the default thing that does everything they need it to do.
Right, and
So
it's like, yeah, pretty approachable, I guess, for like the end user, whereas yeah, ours is a little
yeah,
intimidating at first.
yeah,
Okay,
it's different
cool.
tool.
Yeah, different tool. Got it. Sweet. All right. Well, thank you again so much. This was like an awesome class, and best of luck with the next adventure. And Brian, looking forward to seeing you carry on the legacy. All right. Thanks, guys.
Thank you.
Take care.
Thanks.